cumulative distribution function of a random variable is defined as the probability that the random variable x is less than or equal to the value script x. This probability can be computed for any random variable. So any random variable, whether it's continuous or not, has a CDF, cumulative distribution function. The notation for the CDF is this big f sub x of x. Okay? In particular, we can compute fx of x by doing the summation of the PMF over all values of k less than or equal to x if x is a discrete random variable, or by integrating from negative infinity to 2x the density if x is a continuous random variable. Okay? Now, the CDF, remember, what it's doing is accumulating the probability up to and including the value x. Okay? It carries all the information that the PDF or the PMF carry. Okay? So there's no loss of information when going from the PDF or the PMF to the CDF. In some cases, neither a PMF nor a PDF exists for a random variable, because the random variable may be neither discrete nor continuous. Okay? Which we'll see an example today. In those cases, the CDF is very useful because the cumulative distribution function can always be computed. Okay? We'll consider that case in a few minutes after we study the basics of the CDF. Okay, so let's see the basic properties that follow from the definition of a CDF. First of all, the CDF is between 0 and 1. Why? Because of the normalization of probability, right? Probabilities are between 0 and 1. And the CDF is just a probability, so it should be between 0 and 1. The CDF at negative infinity is defined as the limit as x goes to negative infinity fx of x. Okay, let's understand what that is. Fx of x is the probability that x is less than or equal to x. Now, if we take the limit as x goes to negative infinity, what does that mean? That's the probability that x is less than or equal to negative infinity. That should be 0, right? So we understand from this that a CDF starts at 0. Okay? A CDF rises at most up to what? 1, right? Because of its definition. And in fact, a CDF is always equal to 1 at infinity. Why? Because the limit as x goes to infinity fx of x is essentially the probability that x is less than or equal to infinity, which should be 1. So a CDF fx of x starts at 0 and ends up at ends up at 1 at infinity. Okay? How it goes from 0 to infinity changes according to the distribution. But there is one thing that has to be satisfied, which is that a CDF is monotonically non-decreasing. Okay? Monotonically non-decreasing means it can never decrease as x increases. It can increase or stay constant. Okay? Let's prove this. Yes, please.
Can it jump up?
Yes, it can jump. When do you think it could jump?
There is a linear, discrete.
Probability mass at some point, yes. So we'll address that point. So let's see. The probability that, well, let's first show that when x is less than y, fx of x is less than fx of y. Okay? Now, the probability that x is less than or equal to y, okay, can be broken up into the probability of x is less than or equal to x union x is between x and less than or equal to y. Okay? Whenever x is less than y, less than or equal to y. Right? The probability that x is less than or equal to y is the probability of the union x is less than or equal to x, or x is between x and y. Right? But these two events, by their definition, are disjoint events. So, so this becomes equal to the sum of the probability that x is less than or equal to x and the probability that x is between x and y. This is a probability, so it is bigger than or equal to 0. Right? Therefore, the left-hand side, which is by definition fx of y, is bigger than or equal to this term on the right-hand side, which is fx of x. Okay? Let's rewrite this. Fx of y is bigger than or equal to fx of x whenever x is less than or equal to y. Okay? So let's repeat. When x is less than or equal to x, fx of x is less than or equal to fx of y. What does that mean? The CDF can only increase or stay constant. It is non-decreasing. Okay? Non-decreasing. So the CDF is a pretty monotone function. Okay? It starts at 0 and increases up to 1. Okay? As it's increasing, it may increase fast or slowly sometimes, and it may stop for a while. Okay? But it can never go down and come up again. Okay? Yes, please.
Does the derivative of this function be negative?
Yes, the derivative of this function is actually, as we'll just show, for a continuous random variable, the derivative is the density. Okay? Any questions about the CDF? Okay, so here's another thing about another property of the CDF. CDF is continuous from the right. CDF is continuous from the right. What does that mean? The limit as delta goes to 0, fx of x plus delta is equal to fx of x. So as as we approach the point x from the left, from the right, as we approach the point x from the right, the CDF is continuous. It does not, it cannot jump, okay, from, as we approach from the right. It can jump as we approach from the left. It can have a discontinuity as we approach from the left. Okay, so let's prove this. And while we're proving, we'll also maybe understand it better. So the limit as delta goes to 0, the probability of x less than or equal to x plus delta is the probability of interest. Okay? But again, this can be broken up into a sum. This is the probability that x is less than or equal to x plus the probability that x is between x and x plus delta. Okay? Okay. So as delta goes to 0, this goes to 0. So we find that this is in the limit equal to fx of x. Okay? Now we wouldn't have been able to do this if we had x minus delta here. Okay? If we had x minus delta, we would be approaching the point x from the left. Okay? In that case, we wouldn't have been able to break it into a summation of fx of x plus something else, which is positive. Okay? So that's why it doesn't hold the other way. I mean, a probability cumulative distribution function is not necessarily continuous from the left, but it's always continuous from the right. Okay? So, oh, maybe I shouldn't have erased this. Anyway, we'll do an example later on, and I'll redraw it. Okay? So, what's next? Okay. The probability that x is equal to x, the probability mass at the value at the point x. Okay? The probability that x is equal to x is, of course, the probability that x is less than or equal to x, okay, minus the limit of the probability that x is less than x, well, if you want, let's just do this, minus fx of x minus. What is x minus? X minus is the limit of approaching x from the left. Okay? Now, let's redraw this. This is the point x. This is fx of y, let's say. Okay? So this is my CDF. Now, at this point, okay, I have fx of x. Now, x minus is a number that's arbitrarily close to x, but smaller than x. Okay? At this point, the CDF may not be continuous. Okay? In fact, there may be a discontinuity. For example, let's draw this like this. Okay? There may be a jump such that the value of fx minus is different from fx of x. Okay? Now, let's write this difference. Let me rewrite this. I want to find the difference of fx of x and fx of x minus. Okay? Fx of x is nothing but the probability that x is less than or equal to x. What is fx of x minus?
Probability of x is less than x minus.
Which is essentially the probability that x is less than x. Okay? So this is the probability that x is less than or equal to x minus the probability that x is less than x. Right? Okay? This difference is exactly equal to the probability that x is equal to the value x. Now, this will be 0. This will be 0 whenever x is continuous. The random variable's x is continuous over the whole real line or around the point x. Okay, x is continuous at x. Okay, it is equal to, it is bigger than 0. Okay, when fx of x has a discontinuity, meaning x equals x with some positive probability, which means there's a discrete probability mass at this point. Okay? So whenever the CDF makes a jump, that is because the random variable takes that value with some positive probability. Okay? Excuse me? Uh-huh. So fx of x minus is the probability that random variable x is less than or equal to x minus, which is another way of saying this. Exactly. So it's not necessarily continuous. As you approach x from the left, okay, there may be a discontinuity. As you approach from the right, as we just proved, okay, this function is continuous. Yes, please. No, no, that's not true. Right now, let's just first understand what this says, which is whenever the CDF makes a discontinuity, okay, the amount of the jump is equal to the probability that x takes this value x. Now, when the random variable is continuous, we already showed that the probability that x equals x for any particular value, script x, is equal to 0. Okay? This means when the random variable is continuous, there cannot be any jumps like this. Okay? So for continuous random variables with PDFs, density functions, there are no jumps. Okay? Yes. Right. So we'll address that next. Okay. So let's go step by step. First, let's make sure everybody understands this part. So what have we found about the CDF? Let's summarize. The CDF is a function that starts at 0, goes to 1. It never decreases. It's monotone, non-decreasing. And it's always continuous from the right. Sometimes it's not continuous from the left. When it's not continuous from the left, it makes a jump like this. This point is included. This point is not included. the amount of the jump must be equal to the probability that x takes this particular value. Okay? So far, this is what we have established. Now let's connect this to the PDF. When x is discrete, okay, with integer values, okay, fx of x, of course, is the probability that x is less than or equal to x, which can be found by summing the PMF over all values k less than or equal to x. Okay. So, what kind of function is the CDF? Okay. Px equals x is the difference fx of x minus fx of x minus. So it's the difference between the value of the CDF as you approach from the left and the value of the CDF as you approach from the right. Okay. The difference of the value of the CDF as you approach from the right and the value as you approach from the left gives us the probability at x. Okay, so what do we see when the random variable is discrete? We just see a staircase function. Okay, fx of x, x is discrete. Okay, for example, x takes the values, let's draw a PMF here, px of x. It takes the values x1, x2, and x3 with these probabilities. Okay? Let's call this, this is p1, p2, p3. Takes these values. This is the PMF. Now, what do we have? Before x1, up to x1, from negative infinity, what is the value of the CDF? Let me redraw this. The value of the CDF at negative infinity is 0. Look at x1. fx of x1 minus is the probability that x is less than x1. What is that probability? It's 0. Okay? It's 0 up to x1. But right at x1, fx of x1 is the probability that x is less than or equal to x1, which is suddenly equal to p1, right? So it jumps to p1. Okay? Now, between x1 and x2, what happens? Nothing happens, right? It just stays constant up to x2. Why? Remember, the CDF is just accumulating probability. Okay? The CDF at this point, for example, is the probability that x is less than or equal to this point. But, okay, up to this point, there's only one probability mass at x1. So as you sum probabilities, nothing changes up to this point. But something changes right after x2. Okay? At x2, the CDF jumps to p1 plus p2. Right, so it jumps to p1 plus p2. What is the value of the jump? The value of the jump is p2, because that's the difference between fx2. So let's compute. fx2 of x2 minus fx of x1 is nothing but the probability that x is less than or equal to x2 minus the probability that x is less than or equal to x1, which is exactly equal to the probability that x is exactly equal to x2. Okay? So it jumps to here. It stays constant up to x3. at x3 it makes its final jump. What does it jump to? 1. Okay, and the amount of the jump is P2, P3. Okay, so this is an example of a discrete random variable, and it's CDF. So from here you can easily see that the cumulative distribution function of a discrete random variable is in the form of a staircase function like this. Okay, so piecewise constant jump, constant jump, constant jump. Okay, how many jumps are there? In this case 3, but in general, however, whatever the number of values that x takes. Okay, any questions here? The sum of the jumps has to be 1, right? Right, the sum of P1 and P2 and P3 has to be 1. Why? Because it's the sum of the PMF. Oh no, right? Because that's clearly infinite. Okay, any other questions? Okay, so let's do the continuous case. The continuous case is the opposite extreme. Here we just have jumps followed by constant, in the case where the random variable is a continuous random variable, there are no jumps. Okay, and the CDF is continuous. In fact, another way of defining a continuous random variable is to define it as a random variable whose CDF is a continuous function. Okay? So when x is continuous, it has a PDF, a density. Since this is a probability, this is the probability that x is less than or equal to x, it is found by integrating the density from -infinity to x. Okay? By the fundamental theorem of calculus, whenever this integral exists, this density is equal to the derivative of fx, the CDF. Right? Okay? Since the CDF is the integral of the density is the derivative of the CDF. Okay? As simple as that. Okay? Look at the analogy with the discrete case. In the discrete case, the PMF is found by the differences that the CDF makes at those values. Here, the differences are all incremental because the probability masses are 0. In the continuous case, we have a PDF. The probability of any particular value is 0. So instead of differences, we're looking at derivatives. Okay? So of course, this is valid wherever fx of x is differentiable. Okay? A continuous function is not necessarily differentiable. Okay? So let's leave that aside for the moment. And let's, as an example, study the exponential. Okay? Example. X is exponential with parameter lambda. This means fx of x is equal to lambda e to the minus lambda x when x is bigger than or equal to 0. Okay, let's compute the CDF. Fx of x is equal to the integral of lambda e to the minus lambda x dx from -infinity to x. And that, you can easily show is 1 minus e to the minus lambda x. Okay, x bigger than or equal to 0. Let's plot this. It's one of the smoothest CDFs there are. Okay, why do I say it's the smoothest? Because it's differentiable and arbitrarily many times, right? All of its derivatives exist. Okay, 1 minus e to the minus lambda x. So it's going to go to 1 eventually. And where does it become rising from 0? At 0. Okay, up to 0 it's exactly equal to 0. At 0 it starts rising. That rise is 1 minus an exponential. Everybody knows what an exponential decay is. Subtract that from 1. It goes like this, concave. Okay? Of course, this shape will change with, according to lambda. The shape is a function of lambda. Around x, by the way, this is something useful to know. Maybe I didn't do a good job. Anyway. You should always, when you're drawing a curve like this, you could, compare its slope with the x equals y line, the unit slope line. Okay. So anyway, this is our CDF. Okay, so there are no jumps, which makes sense because if there was a jump, it would mean x takes on a particular value with a non-zero probability, which is in this case not true. Any questions? How about the CDF of a uniform random variable? X is uniform between A and B. How does its CDF look?
Slope is constant.
What is that slope equal to? The slope is exactly the PDF, which is 1 over b minus a. And it starts rising at a, and it rises up to b. Rises to 1 at b. So this is the CDF. As you can see, there are discontinuities, okay, in this case. There are no discontinuities. There are discontinuities in the derivative, okay, which is the PDF. There are points that are where the CDF is not differentiable. Okay. Okay. So let's consider a geometric random variable. This is interesting. We haven't talked about the geometric random variable for a while, of course, except from the aside from the exam this morning, maybe. The geometric random variable is actually very similar to the exponential random variable, such that we can almost say that the geometric is the discrete counterpart of the exponential. Let's see what this means. Okay. In order to do that, let's write the CDFs of both random variables. The nice thing about the CDF is it allows us to compare, it's computable both for continuous and for discrete random variables. So that's why it's universal. In fact, in higher, more advanced classes of probability, the CDF gets to be used much more than the PDF. Okay, not in this class, but so the CDF of a geometric. So let's see. Let XD be geometric. D stands for discrete. With parameter, well, how many parameters does a geometric have? 1, and that is the probability of success, P. Geometric with P. What is the probability? What is the probability that X is less than or equal to K? An easy way of thinking about this is writing this as 1 minus the probability that X is bigger than K. X is bigger than K means the number of trials up to and including the first success is more than K, which is equivalent to saying that the first K trials have resulted in failure. Okay? The probability of that is 1 minus P raised to the power K. Okay? So the CDF is this. So let's write it down again. Fxd of K is 1 minus P to the K. But I would like to express this as an exponential. So I can simply take the logarithm of this and raise it to the power e. I mean, use it in the, so basically write 1 minus e to the power natural log 1 minus p to the k. Right? I can always do this. 1 minus p to the k is always positive, so I can always take its natural log. Okay? And take e to the log 1. What does that give me? That gives me 1 minus e to the k times logarithm, if you want, 1 over 1 minus p, and put here a negative sign. Okay? Now compare this by fx of x, where x is exponential with parameter lambda. Fx of x is 1 minus e to the minus lambda x. Okay? In other words, e to the minus x lambda. So, you see the similarity. We have 1 minus k, 1 minus e to the minus k times a constant. This is a constant. Versus 1 minus e to the negative x times a constant. Okay? So the example tells us to select p as 1 minus e to the lambda delta. Okay? Select p as 1 minus e to the lambda delta. Okay? What happens to ln 1 over 1 minus p? Natural log of 1 over 1 minus p is natural log of e to the minus lambda delta, right? Which is negative lambda delta. Okay? So, let's write this here. So this would be 1 minus e to the minus k, let's see. Did I make a sign error somewhere? I think we should have selected p as 1 minus e to the negative lambda delta. That would work, because this would be then, no. Oh, okay. This would be then positive, and this would be positive as well. So we would have e to the minus k lambda delta. Okay? So you see now the similarity. This CDF is a function of k. As a function of k, it rises like 1 minus e to the minus k lambda delta. Okay? In other words, 1 minus e to the minus lambda times k delta. Okay? You see the similarity is becoming more and more obvious when you compare this with this. Here, I'm going with discrete units of delta. Okay? As delta goes to 0, I will be tracing real numbers when k is an integer. Okay? K times delta is becoming smaller and smaller. Okay? And it's an approximation for this x. Okay? So let's, maybe this will make more sense when I sketch them side by side. Let's erase the uniform CDF from here. Okay. The exponential goes like this, to 1. Okay. This is fx of x, which is 1 minus e to the minus lambda x. Okay. On the other hand, fxd of k, how does it go? Goes like this. Oops. Goes like a staircase. But it looks very similar. And it also goes up to infinity. It reaches infinity at 1. I'm sorry, it reaches 1 at infinity. It reaches 1 as k goes to infinity, right? Because the geometric PDF takes an infinite number of values. It takes values at all integers from 0 to infinity, right? So it's a staircase that is approximated by the exponential when you choose, basically make this, this approximation. Okay. I recommend that you study this example again on your own. Okay. So the purpose of this essentially not only is not only to, of course, study the properties of the CDF, but also it's useful to note that the exponential is a continuous counterpart of the geometric. Okay? Where did we use the geometric when we studied discrete random variables? To model events where at every trial the probability of success is independent from the past, right? No matter how many failures I've had so far, I'm starting again and my probability of success at my new attempt is p. It doesn't change. Okay? It's as if everything has been reset, okay, and I'm starting at time 0. Okay? The geometric measures the length of this process. Okay? How long will I try until I succeed? Okay? The exponential works the same way. The exponential is memoryless, just like the geometric. Given that the lifetime is bigger than a particular value t, what is the probability that it's bigger than t plus t1? It doesn't matter how big t is. So it doesn't matter how much time has passed. Okay? The probability that the random variable x will be bigger than x plus t is exactly equal to the probability that, given its x is bigger than t, let me write it here. The probability that x is bigger than t plus x, given that x is already bigger than t, is equal to the probability that x is bigger than x. Okay? So no matter what happened in the past, the exponential loses its memory and continues as if it's starting from 0. This is called the memorylessness property. The exponential distribution is memoryless. The geometric is also memoryless. Okay? So we'll explore this later on. Okay. So let's do a final example. It's a good one. The CDF of the maximum of a number of independent random variables, independent and identically distributed random variables. So you're allowed to take a certain exam n times. Okay? Let x1, x2, up to xn be the grades you get from these exams, from each of these trials. And assume that the grades are independent and identically distributed. So you don't improve yourself from exam to exam. Your chances of getting each score is the same at every exam. Okay? You take these exams. Okay, so basically the difference between the exams is just a matter of luck, you could say. Okay? And they will take the maximum of your scores. It's a good deal, right? Why do you think it's a good deal? Because the maximum tends to be bigger than all the scores, right? So if you have a certain distribution for your score x, x1, okay, the distribution of the maximums will be better. The distribution of the maximum score will be better. So let's see how that works. Find the CDF of your final score in terms of the CDF of one exam grade. Okay, so in the example, let x1 be the grade you get from exam 1. Taking this exam for the first time, your grade is x1. And fx1 of x is the CDF of x1. Now the final score, x is the final score. The final score is computed by taking the maximum of the n random variables, x1 up to xn. We are interested in finding the CDF of x, the final score. What is the CDF? CDF is nothing but a probability. And we know how probabilities work. The CDF is the probability that x is less than or equal to x. Okay. In other words, the probability that the maximum of x1 up to xn is less than or equal to x. What does does this mean? If the maximum score is less than a value, that means all the scores are less than that value, and vice versa, right? The maximum is less than x if and only if all the scores are less than x. You see this? Okay. So this is the probability that x1 is less than or equal to x, and x2 is less than or equal to x, and xn is less than or equal to x. But what do we know about the scores? We know that they are all independent. Okay? So the probability of the intersection of these events is the product of the probabilities. The probability that x1 is less than or equal to x times the probability that x2 is less than or equal to x times the probability that xn is less than or equal to x. Okay? So, in summary, well, x1 is equal to less than or equal to x is the CDF of x1, evaluated x. This is the CDF of x2. But they are all identically distributed, right? They have the same CDF. Okay, have the same CDF. So this product is nothing but the CDF of one of them raised to the nth power. Okay, so this is fx1 of x raised to the nth power. Okay. So let's see what happens graphically. Suppose this was my, let's see. Let's first sketch a CDF for my score from one exam. Okay? Suppose it's not likely to be very high. So it's concentrated. So this is maybe 100, the maximum score. Okay? And of course, my grade will be below 100, below or equal to 100 for sure. So my CDF reaches 1 at that point. But suppose my CDF is really concentrated around here in the 20s. Okay? So let's make something like this. Suppose this is the case. This is fx1 of x. What happens when you take this function and raise it to the nth power? What happens, do you think? Right. It approaches, I mean, it becomes, maybe when you square it, it may go like this, and then it goes like this, right? It tends to lose, basically, let's see. It's not always going to, maybe this is not a great, so do this with a specific PDF as an exercise. We could have done it with the exponential, but the exponential will not be going to 1 at 100. So the bottom line is, as you take the nth power, it tends to get concentrated around higher and higher values. So the CDF improves. You tend to expect a higher grade. Okay? So let's just say it goes in this direction. Okay. So as a final exercise, I want to just give you the description of a random variable which is neither continuous nor discrete. And I would like you to think about the CDF of that random variable. So here's the description. x is equal to 0 with probability 1/2, and it is uniform between 1 and 2 with probability 1/2. Okay? X does not have a PMF, right? And it doesn't have a PDF either. But we can draw a CDF for this random variable. Does anyone want to help me draw this? It's 0 up to 0, right? And what happens at 0? A jump from here to here of size 1/2. And then what? Stays constant up to 1. Between 1 and 2, there is a rise. Okay, because probability builds up. Up to what? Up to 1 after 2. Okay, this is the CDF of this random variable. Okay, we'll take it from here next time.